So today we are going to summarize the thermodynamics of mixtures, the real mixtures, ideal mixtures, and their relationship to one another. In the middle of the board we have the ideal gas law. I will first start from the ideal gas law, make it to a van der Waals equation of state, and that concept relates how we treat the real mixtures and how we incorporate the non-realities, non-idealities into the real mixture behavior. So those of you who have been watching these videos will remember that we have two major assumptions in the ideal gas law. One is that the volume occupied by the molecules is negligible in relation to the total volume of the gases that occupy. And also the molecular interactions are negligible, that the molecules act like billiard balls and they don't interact. They don't have attractive repulsive interactions with one another. However, for the real fluids, we need to correct this by taking care of the volume occupied by the molecules. The first correction we introduced, indeed, it was introduced by van der Waals, was to take care of the volume occupied by the molecules. So this volume is the total volume. By subtracting the volume occupied by the molecules, we are estimating the volume of the void. The second correction we introduced was for the molecular interactions, the attractive forces between the molecules. And this required at least two molecules, hence we have V square as a reciprocal term, or density square as the multiplier. Now when we just make this correction and translate the ideal gas law to a real fluid behavior equation of state, van der Waals equation of state, this is a representative of the cubic equations of states, and cubic equations are our favorite in making predictions of vapor-liquid equilibrium for the pure fluids. Now we're going to translate that into the prediction of the behaviors of the mixtures, hence the title, Thermodynamics of the Mixtures. Now we have, again, like the ideal gas and real fluid behavior, we have ideal mixtures and real mixtures. And so far we have made the definitions of the ideal mixtures in relationship to the real mixtures in terms of how they behave when we mix in terms of their volumes, how they behave when we mix in terms of their energies. Now, this term, remember, that was taking care of the volume occupied by the molecules and was introducing a correction to the real fluid behavior. And it was important as we were compressing the gas and the molecules were approaching closer to one another, and their volume would become relatively important relative to the total volume. Now, let's discuss the ideal mixtures. When the mixtures, think about two ideal gases, mixing two ideal gases. The molecular volumes are not important, the molecular interactions are not important. When the molecular volumes and molecular interactions are not important, you're just mixing two void volumes. And adding those two void volumes should be additive. Hence the Dalton's law, that we add the volumes of the ideal gases, their partial pressures are proportional to the mole fractions, their fractional volumes are proportional to their mole fractions in the gas phase. Ideal gas mixtures, in most situations, are ideal mixtures. The volumes are additive. But when we are mixing two real fluids, and think about large balls and small balls mixed together, the smaller balls are going to fill the voids of the larger balls, and even though we start from, say, two equal volumes of large balls and small balls, when we mix them, the total volume is going to be smaller. Or if we have two molecules which experience repulsive interactions, that they will need more volume than their starting initial volumes. So when we mix ideal fluids, their volume will be additive, or the volume change upon mixing is going to be zero. When we mix real fluids, we are going to have positive or negative deviation from the ideal, that we will have a volume change upon mixing. Similarly, when we mix two ideal fluids, when there are no attractions and there are no molecular interactions, such as represented by this term, we will have no energy release due to mixing. But if there are attractive forces or repulsive forces, those forces will come into play, and the ending mixture is going to have either more or less energy than the starting molecules, and hence we are going to have an enthalpy change upon mixing. The volume and enthalpy parameters that we have in thermodynamics being zero for ideal mixtures is relatively straightforward. But on the other hand, we also have an entropy term. The entropy term is going to be non-zero even for the ideal mixtures. All right, so the ideal mixtures, meaning billiard balls, for example, that we are going to have same size billiard balls but different colors. So you're going to have a container full of white billiard balls, another container full of blue billiard balls, and we are going to mix them together. Eventually, those balls will be randomly mixed, and when we play the game of statistics, and when we have a bag mixed full of those mixed billiard balls, if you had just one container of white billiard balls, finding a white ball in that container, the probability would be 1. Same for the blue, but when they are mixed together, the probability of finding one white ball will be proportional to its concentration in that container. So the entropy change upon mixing, as we derived earlier, is going to be minus R ln xi, and of course if you have a large number of components, this is going to be represented by, for the total system, as given by the equation. And when we take this equation and substitute in the definition of Gibbs free energy and Helmholtz free energies, we'll have delta mix G for an ideal mixture to be equal to minus plus RT sigma xi ln xi, and delta mix A will be RT sigma xi ln xi. All right? So, even when we have ideal gases mixing together, we're going to have an entropy change due to the fact that now, instead of pure components, we have mixtures, and probability of finding one molecule in any coordinate is no longer 1 and is proportional to the concentration. and that is reflected, of course, through the definition of Gibbs free energy, which is H minus Ts. All right? So even though we don't have any enthalpy change, because our mixture is ideal, we're going to have a change in entropy, which is reflected in the Gibbs free energy. And these are going to be, of course, reflected here with the additional effects coming through volume change and enthalpy change. So with that, now we are going to have a large set of equations to work with, but we still have to be able to, starting from an equation of state, knowing these facts about the mixtures, real and ideal, we still have to be able to have a reasonable approximation to be able to predict vapor-liquid equilibrium behavior and chemical equilibrium behavior. Now, the vapor-liquid equilibrium behavior is going to be our primary concern, and before we jump to the estimations of the vapor-liquid equilibrium, let's remember what we could estimate with a cubic equation of state for a pure fluid. For pure fluid, this ideal gas law, PV relationship was simply reciprocal, but the cubic equation of state, not just van der Waals, but any cubic equation of state or a virial equation of state, enabled us to predict vapor-liquid equilibrium of pure fluids. If I have accurate values for A and B, this equation, if I substitute values for V, is going to give me an S-shaped curve for PV behavior, and this S-shaped curve can be used. Of course, this is an isotherm. I'm able to draw this line for a constant temperature. And this S-shaped behavior, once cut through a line that goes through equilibrium pressure, is going to give me equal areas in the functional behavior above and below the line, with which I can estimate the liquid and vapor volumes. And when I do this for a number of isotherms, I should be able to construct the vapor-liquid coexistence envelope. And here I have the critical point. In between, I have vapor-liquid equilibrium. So I can estimate vapor-liquid equilibrium of a pure fluid using van der Waals equation of state. Now, could it be possible that if I can make good enough estimates of A and B, would I be able to estimate vapor-liquid equilibrium of the mixtures? But let me remember the equilibrium condition. The equilibrium condition, as we have derived already, applies here also in that small example that I have sketched up here, that if phase 1 let's call this phase 1. And phase 2 are in equilibrium. Their temperatures should be equal. That their pressures should be equal. For the pure fluid, that their Gibbs free energies should be equal, right? Molar Gibbs free energies should be equal. When we take the pure fluid domain, not to be mixed by the mixtures, so here we are in desperate need of being able to estimate the vapor-liquid equilibrium of a mixture. So let's just keep our mixture manageable. Let's keep our mixture a binary mixture of A and B, and mole fraction of B is increasing in that direction, and this is the boiling point of that mixture. Here we have another dimension. On the two-dimensional surface we can only plot so much, so we're going to keep the pressure constant. In that constant pressure domain, let's have our low boiling component here. This is the boiling point of A. This should be the boiling point of B. And between the two, we are going to have, if this is a well-behaved mixture, we're going to have values in between that looks like this. So this is the bubble point curve. On the other hand, when we have a mixture in the vapor phase and it is condensing, it is going to condense at a different temperature than the bubble point because of the mixture behavior, additional factors that comes into this picture because of the mixture behavior. We're going to have a different curve which is called the dew point curve. All right, and again we have a mixture of liquid and vapor here, we have pure vapor here, we have pure liquid here. Similar, but not that similar, all right? Similar, we have pure liquid here, we have liquid and vapor mixture here, and we have vapor here. Now, in that mixture domain, we are going to have, for a system to be in equilibrium, a vapor-liquid system to be in equilibrium, we're going to have, again, same conditions, equality of temperatures, equality of pressures, all right? So it means that when I'm talking about equilibrium, I'm talking about a horizontal line here, all right? So this is my equilibrium line, all right? This is my vapor, and this is the liquid in equilibrium with that vapor. And equality of the partial molar Gibbs free energies of all the components. So that we can have equilibrium. And these partial molar Gibbs free energies are also known as chemical potentials. So we have however many components we have, we can write these equalities for those. Now we are going to start from this point, and we are going to establish mathematical tools to be able to predict the vapor-liquid equilibrium behavior of a multi-component mixture, but to begin with, of a binary mixture, and its bubble point, dew point curves. So, remember, we translated the chemical potentials, Gibbs free energies, to terms like fugacities, but before we come back and estimate the fugacities for real mixtures, even when they are ideal, all right, let's just remember what we were doing here. The equality of the Gibbs free energies at the thermodynamic equilibrium condition was established so that we have equality of the fugacity coefficients. Let's define the fugacity coefficient. Fugacity coefficient was, for a pure component, F over P. We were referencing the fluid relative to an ideal gas, F over P, or relative to an ideal condition. So the fugacity of the vapor should be equal to the fugacity of the liquid all right, and the closest approximation of the fugacity of a liquid was its vapor pressure, and we were going to make sure that the fugacities were equal. Since this was a pure fluid, the pressures were going to be equal, the fugacities were going to be equal, so the fugacity coefficients were going to be equal. From here, we need to develop rules to estimate the fugacities of the individual components in a mixture, as well as fugacity coefficients of the individuals in a mixture. In a mixture, our terminology is going to be different in order not to make, in order not to confuse terms. Here, the fugacities were function of temperature and pressure for pure fluids. But for mixtures, fugacities are going to be functions of temperatures, pressures, and mole fractions of all components. All right, fugacity of any component. And since this is not in fugacity of the component in the pure form, but in a mixture, we're just putting an overbar to make sure that we differentiate this Fi from this Fi, because we will need that eventually. The fugacity coefficient of the mixture is going to be Fi, but this is going to be relative to its pure component, Xi times Fi of TMP. All right? So this is the general approach that we are going to take, and how we are going to calculate these fugacities are going to be detailed in mathematics, but let's just start from this fugacity coefficient definition. Let's again carry the discussion back to the pure fluids domain. Hopefully it's easier to understand in this domain, and bring what we deduce to here to make some initial approximations. Now, if my fluid is close to an ideal gas, here you see a reciprocal relationship between P and V starts to appear, meaning at low pressures and high temperatures, we might have ideal gas behavior. So if we have an ideal gas behavior, close to ideal behavior, close our eyes to the liquid side for a moment. What will be the fugacity coefficient of the vapor? In the ideal gas state, our pressures, our fugacities will approach to the pressures, and under ideal gas conditions, our fugacity coefficients will be approximated to 1. As a result, our fugacities would approximate to their pressures. So what would we expect for a mixture of an ideal gas? For a mixture of an ideal gas, again, the fugacity coefficients must be close to unity. All right, and we are expecting that ideal gas mixtures behave ideally, large volumes, no molecular interactions, no attractive forces, and so on and so forth. So we're going to have close to unity fugacity coefficients, and the fugacities of that component in the mixture is going to be xi times fi TnP. But remember, this was equal to its pressure, so this should be equal to xi times pressure. Now we have derived what is broadly known as the Dalton's law. So on the vapor side, if we can represent the fluid behavior equivalent of an ideal gas mixture, ideal mixture of ideal gases, we can approximate the fugacities as such. Otherwise, we have to take care of the fugacities of the pure components. We have to take care of the fugacity coefficient and make accurate estimations of this fugacity coefficient by taking the proper integrals of the partial molar Gibbs free energies and obtain accurate estimations. So on the side of the vapor condensations, we might approximate our system like this. Now, what happens on the liquid side? Liquid side is a little bit more difficult to handle because when we are in the liquid state, molecules tend not to behave ideally for a broad range of components. Now let's take this expression phi I, fi, and proportionality constant between the pure component fugacity and its contribution to the liquid state. So in the liquid state, having unity fugacity coefficient is not always possible, but let's first take that and continue here for the liquid side. The fugacity, which is a function of temperature, pressure, and mole fractions of all the constituents, should be equal to fugacity coefficient of the liquid side times mole fraction times fugacity of component I at this given temperature and pressure. Now the fugacity of the component I, pure component fugacity of component I in the liquid state, can be approximated by the vapor pressure of the fluid. The fugacity coefficient on the liquid side can be reduced to 1 for close to ideal mixtures, and on the liquid side we have an expression giving us the fugacity of the component I in the liquid phase. This is in the vapor phase, and let me just switch the terminology from X to Y, not to mix the vapor mole fractions with the liquid mole fractions. Now, at equilibrium, their temperatures must be equal, yes. Their pressures must be equal, yes. Now, Gibbs free energies, partial molar Gibbs free energies, or translated into the new term as fugacities should be equal. So when we take the equality of those fugacities from the liquid side, we have what is called as the Rolle's law. This is Dalton's law. They're going to be equal to one another at the point of equilibrium. Now I'm going to combine those two equations plus one more to be able to estimate bubble points and dew points. FIL is equal to XI PI vapor, FIV is equal to YI times P total, and they're going to be equal to one another. So now we have an ideal mixture evolved into an equation. The only unknown here is the effect of temperature on the vapor pressure of a liquid. The effect of temperature on the vapor pressure of the liquid is well known, right? As the temperature increases, vapor pressure increases. But we need to have an equation to be able to easily handle the analysis. Now, the thermodynamically consistent approach for this can come from the Clapeyron, or even more approximate but straightforward through Clausius-Clapeyron equation. And if you remember, Clausius-Clapeyron equation allowed us to relate the vapor pressures of the fluids to their heat of vaporization. So with that, if I know the vapor pressure of my fluid at only one temperature, or if I know the boiling point of my fluid at only one pressure, all right, I can, and if I know the heat of vaporization of that fluid, I can get infinitely many values for the temperature vapor pressure pairs. So Clausius-Clapeyron equation relates my vapor pressure to its boiling point through the heat of vaporization data. Two assumptions that we have made when deriving this Clausius-Clapeyron equation. One was that heat of vaporization was independent of temperature, or for that matter, pressure. That was one assumption. The second assumption, coming to here, made was that the vapor side of the process can be approximated through the ideal gas law, right? So when the conditions are such that those assumptions are not valid, our estimations will be a little bit, sometimes a lot, off from the true experimental behavior, but still this equation gives us a starting point. Now what are we going to do? How are we going to estimate the bubble point curve? Estimation of the bubble point. Let me generate a bubble for the bubble point calculations, not to be mixed with the other. So bubble point is when we are approaching equilibrium from the liquid side, when we are heating our liquid to a temperature where it is going to boil. So we know the mole fractions in the liquid phase, and the total pressure is known. But we don't know the vapor that is in composition of the vapor that is in equilibrium with that liquid. So this is our XB. We would like to find what would be the temperature where I'm going to have a vapor at a composition that I know is going to boil at this pressure. If this is my composition, what is the temperature at which this liquid is going to boil with a vapor whose composition I don't know? But I know my equilibrium conditions, all right? My equilibrium conditions dictates that each of those components should have identical fugacities. Identical fugacities. But I don't know this, so I'm going to start a trial and error procedure. First, I'm going to estimate Yi for each of those components. I know the mole fractions. I can calculate the vapor pressures by choosing a temperature all right. When I choose a temperature, I know the vapor pressure through the Clausius-Clapeyron equation. I know now, given the temperature, I know the pressure, I know the mole fraction, I know I can calculate Yi. After calculating Yi's for all the components like this, I will just check if summation of Yi is equal to 1 or not. If it is greater than 1, it means that I have to decrease the vapor pressures. It means that I have to decrease the temperature a little bit. If it is less than 1, it means that I have to increase the vapor pressure. It means I have to increase the temperature a little bit and go back. All right? So instead of doing this arbitrarily, we might choose to have a calculated estimate of the new temperature. how can we calculate this new temperature? So summation of yi different from 1 means that our total pressure is different from our intended total pressure, and we are going to make a correction for the mole fractions in such a way that our P total is going to be the intended total pressure, readjust the vapor pressures accordingly, and start with this newly selected temperature. This is for the bubble point estimations. For the dew point estimations, let me generate another balloon. And start from the point that yi is known, are known. Again, P total is also known. Again, we choose a temperature. Again, we have the Clausius-Clapeyron equation that is going to give us the vapor pressures, but now that P total and yi are known, given the temperature, we are going to calculate xi. All right? And we are going to do this for all the components, and we are going to check if the summation of all the component mole fractions estimated as such is equal to 1. If not, we are going to rescale the temperature and we will reiterate. Okay? So both bubble point and the dew point calculations are iterative expressions. Iterative operations. All right? We will iterate until we have close to 1 mole fraction summations. This test is a test on our material balance. All right? This test is on our material balance. So for ideal mixtures of ideal liquids and ideal gases, now we have a tool to estimate vapor-liquid equilibrium. What if the liquid were not ideal? If the liquid were not ideal, we had to take care of the Fugacity coefficients accurately. we have to take care fugacity coefficients accurately. We have to take care of the pure fluid fugacities accurately, and classical approach is to use the activity coefficient. So if we are going to estimate the vapor-liquid equilibrium of mixtures, of non-ideal mixtures, through fugacity coefficients on both sides, we call that phi estimations. That we are estimating fugacity coefficient of the vapor, fugacity coefficient of the liquid through an equation of state. This is phi estimation. If we estimate on the vapor side the fugacity coefficient, but if we estimate using the activity coefficients, all right, then the estimation is called phi gamma estimations. So this rounds up the conceptual approach on how we are going to make the estimations of the fugacities and estimations of vapor-liquid equilibria, starting from an ideal mixture example. Would have set the scene a little bit, to set the basis a little bit more easily. Then we are going to go into the detailed mathematics of making the estimations of the activity coefficients and making the estimations of the fugacity coefficients.